the reduction of iron ore in blast furnace. So, this figure shows the various reactions which are occurring in the blast furnace. As we you know, there are various regions, the throat region, as we said, throat region, stake region, belly region, boss and hearth. So, now we would be talking one by one about these, what sort of reaction that occurs. So, this is actually distant from the TUL level. So, we are talking where the combustion occurs, and this is from at the top from where the charge is material is getting charged. So, this is the top region, the stake region. So, in this region gas temperature, top gas temperature is 250, but really it is going somewhere from 7800 to 250. So, this region most of the your water get evaporated. So, free moisture and chemically bonded moisture get evaporated, and some of the reactions we will you will see in the other slide. So, mostly Fe2O3 or hematite reduced to magnetite in this region, and then magnetite to FeO. This is sort of an inactive zone in between, and this indirect reduction takes place, FeO with CO, the reducing gases which are coming out from here, which is CO mostly, which gives a reduced FeO iron oxide into iron and CO2. Though we have put in terms of FeO, but stoichiometrically is not the correct representation of iron oxide. Oxygen contents vary from 0.95 to 1.05. So, usually you write it FeOx. So, the zones in the blast furnace can be divided upper zones, middle zone, this is the middle zone, and this is the lower zone where direct reduction of carbon is taking place. We will describe this in the next slide. So, these phenomena which we described in the previous one, this occurred almost 3/5 height of the blast furnace from the throat region. So, most of the indirect reduction and in fact the decomposition of carbonate except the calcium carbonate, the magnesium and other carbonate, this occurs in this region, and this height if you will look at almost the 3/5 of the blast furnace where the all these phenomena are occurring. So, till end of the stake region the diameter of the furnace keeps on increasing to accommodate the expansion of gases and swelling of the charged material. Fusion and contraction of slag and metal start in the belly region as we discussed before, and melting of slag and metal occur in the boss region. Most of the direct reduction reaction occur in this region which are endothermic. So, as you can see these are the reactions which are occurring in this, and all of them actually are endothermic as such. So, TULs are located about 50 centimeter below the upper rim of the hearth, as we I mentioned during the design of the blast furnace, that TUL location is about 50 centimeter below the upper rim of the hearth. So, along the periphery where combustion of coke occurs, metal and slag tap hole are located about 1 and 2 meter away from the hearth bottom. So, if we now look at the various zones in the blast furnace in terms of reaction, what we will see in the first one in the upper zone, which is known as also the preheating zone. So, vaporization of free water and water of crystallization, that is the chemically bonded water, that occurs usually this is around 150 and this can go up to 400 degrees Celsius. Then decomposition of carbonate occur other than calcium carbonate, because that occurs at higher temperature, So mostly magnesium carbonate or other manganese carbonate, these occurs in this region. Even if you have a carbonate iron ore, that also occurs in this region. So carbon deposition reaction can occur in this region, where CO decompose it into CO2 plus C and gives that carbon. So that carbon deposition reaction, what called solution loss reaction, is also occurred in this region. And partial or complete reduction of hematite to magnetite or boostite. So some boostite also get reduced from hematite to boostite. Boostite is again FeOX. So because the stoichiometry oxygen content is different, but it goes into the series. It reduces first hematite, then magnetite, and then boostite. So in the sequential form. So again in the upper zone, where as I said the temperatures go up to 800 or so. So the sort of a utilization of carbon monoxide, or in terms of percentage of carbon monoxide efficiency, this is 100% is goes the first from magnetite from hematite to magnetite in this region up to 873, means about 600 degrees Celsius, and then magnetite to FeO, its efficiency is about 80% of CO utilization, and this reaction a little bit it occurs in the stake region actually, a middle one, not that much into the upper zone, but some amount can occur which has a 30% CO utilization. And as we said, the solution loss reaction or Woodard reaction, it is sometimes known as, occurs in this region. The efficiency, when we talked about the CO, it's given by this percentage of CO2 divided by total percentage of CO plus CO2 in the gas, 100. So first three reactions are known as the indirect reduction of iron oxide. As you can see, indirectly it's reducing through the gas. And the middle zone reaction, the main reaction again some magnetite to boostite, it reduces, and from boostite to iron. So most of the iron get reduced in this region, but not all, maybe up to 70% or so, and the calcium carbonate decomposes in this region, and this CO2 react with the carbon and form CO again, and even the whatever some moisture is there, that also react with the CO and keep CO2 and hydrogen, and as you know, hydrogen is a much better reductant than CO. So reducibility of the gas increases by this hydrogen. So this reaction is also known as the water shift reaction. So these sort of the reactions occur in the middle zone, and in the lower zone of the blast furnace we have these reactions. These all reactions are endothermic first. So calcium carbonate decomposition, whatever is left from the middle zone, it decomposes in the lower zone, which has a very high temperature range, 1500 or so, and direct reduction of FeO occurs in this region. So as you can see, with solid carbon, FeO is getting converted into Fe. Even SiO2 reduction occurs in this, and the silicon vapors can form, and this is the one which contributes toward the high silicon in metals, and it get absorbed by the liquid iron. manganese get reduced, manganese oxide get reduced into manganese. Similarly, phosphorus pentoxide get reduced to phosphorus. Again, if there is a sulfur associated with iron, it goes with lime and form calcium sulphide, and iron get reduced in that, and the combustion it said occurs in this region also, and that this is the oxidation you can see it, and as it leaves the residue region, it react with the remaining carbon and form the CO. So, this is the only reaction which is exothermic and produce quite a lot heat, but when it react with excess carbon, CO2 plus C equal to 2 CO, that is again an endothermic reaction. So, one has to see the net heat what is released from that reaction. And so, coming to the another part of the, so before anyway coming to the dissection of this, so these are the main important reactions which are taking place, and one has to be very careful, especially with the silicon pickup, this reaction, and this is very important reaction in the blast furnace. Mostly what you need a less silicon in the hot metal, otherwise it leads to desiliconization, another operation after the metal is tapped. So, that is again an expensive one, and it is sort of increase the cost of the steel. But these are the few reactions which we will discuss in detail, similarly about the phosphorus and sulfur at the later stage, and how do they affect the chemistry of the liquid iron and slag and the further processing. So, now I will come to the next topic of dissection of the live blast furnace. Whatever we have discussed till now, we got most of the knowledge from the dissection of live blast furnace. Before that, the blast furnace used to be considered as black box. So, it used to be considered black box because it is all enclosed and it is very hot inside, one cannot see anything what is happening, it is just a speculation. Okay, this is the thing which could happen, a cold model study or like that, and nobody was sure what is happening inside of it, how the various sections look like. We say the cohesive zone, we say the middle zone, we say the stake region, then we say about the tuya region, but what is happening there, really nobody knew about it. So, till the dissection of live blast furnace came. So, people especially in Japan and USA in fact is probably the first one who put it, and then Japan actually started that. They quenched the blast furnace, the live blast furnace, the operating blast furnace, and the quench is using water or nitrogen from the top, and then they dissected it, opened it, and these are the actual operating blast furnace. And in Japan, many blast furnace, almost 10 to 12 blast furnace in one go they did it. And the next few slides will show you some important findings what they have obtained from this, and you would be amazed to look at the different region which they have got it. And this whole study is about 3 to 4 decades old, and the blast furnace since then has improved a lot, and that is what we discussed in the previous slides about the modern blast furnace. But before that, what was the status of the inside status of the blast furnace, you can see in these figures. So, this is the inside arrangement of dissected blast furnace. As you will see, this is the Hirohata blast furnace. This is Kukai blast furnace of Japan, and these are different blast furnace. I am not going into the detail of these operation, but because they were operating with a different raw material, different operating condition, different flow rate, blast rate, and different conditions, which of course can be seen in the literature. One can read those, but what it is pointing out, see, when they operate in a different way, the cohesive zone, this is actually a cohesive zone which is like a semi fused iron and slag and coke layer, and here this is the cohesive zone. A very big difference between these two. While this is extend up to the stake region on top of that almost, and this is just below the stake region. And beside that you have in fact the layer of this fused mass, which is like your fused iron and coke, that has extended till TUL level in this one, while this is quite away, which normally ideally we expected. So, and this is due to the irregularities, and this furnace is not operating in a proper way. You can see also escape hole in this. So, which is clearly showing the furnace is not operating with 100% efficiency in a good form, and you are getting various things in the furnace over here in comparison to this. And but this shows the arrangement, how it is coming at you. Look at closely, as you can see, this is actually the ore, raw material, which could be sinter, pellets, or iron ore, flux, and this region, the white one, is coke. So, alternative layers, they are coming, and you can see these are getting fused and narrow, the layers of raw material except the coke, and when it reaches to this high temperature zone, your ore becomes semi molten in the region, or mushy zone, what you call it, but this white zone, the coke retains its structure. So, most of the gases then passes through this, because they cannot pass through the mushy zone due to very high resistance. So, this there is a permeability issue here. So, structure of cohesive zone is very important, because this is the one which is letting air go out into the other zone and the reducing zone. So, that is why cohesive zone is a very important one, and on which it affects the permeability of the bed and further reduction in the upper zone. So, this clearly shows how they are arranged in this way, escape holding and other thing. If you look at this figure, you can see also it changes, the cohesive zone nature is changing. This is one TUL number, but it is about 14 centimeter in diameter. This is 12 centimeter diameter. So, how the diameter is affecting the cohesive zone and how this layer structure is taking place. Similarly, you can see in this one. In this one, in fact, there was no gas through one TUL. So, this is unused. So, your all fused mass has come up to here. So, there is no direct melting has occurred. It has come till TUL region, and TUL region is really in the hearth. So, you can see it quite a lot. FeO is directly entering into the hearth region. This is 7 centimeter diameter TUL, and that is how the, so this is our softening zone, and various zones are there. So, this gives a very good idea how inside of the blast furnace look like when you quench it and dissect it, and based on that many studies have been taking place, and it has been improved, and that is how the modern blast furnace look now. This again about the dissection of that blast furnace, and when they look at the raceway region, because that is a very important region on which the whole reduction, permeability, aerodynamics of the blast furnace depend. So, you can see when gas is injected, the immediately in front of the tuyer there is a region where there is no coke, it is a cavity, what we call raceway. Then you have a different type of coke. So, just after that there is a high large brown roundish coke, you get it, and this is sort of a racing around that, and that is how the name is raceway. And then you have a finer coke, actually finer and dense coke. So, permeability is less there. So, somehow one has to get rid of that, and this also later on extend to for the dead man. This actually region is a dead man. And then you have a other different types of coke, angular, large brown coke, and then brown dark coke. And if you look at the top view of that, you can see the oxygen level is almost by middle of the raceway 0 oxygen. So, all oxidation reduction has occurred by this. So, this is the one which is oxidized region, and after that reducing gases start. So, CO2 form react with carbon and CO started forming, and front of that raceway you have a more higher size coke, and side of it, because lots of abrasion and other thing is occurring here. So, fines are generated which get deposited further down on that one. So, this is a typical stage of the blast furnace raceway of the quenched one, and this is again I would say 4 decade old, and many things have changed. So, lots of attention is paid now on the coke quality due to this, because you do not want lots of disintegration and generation of fines and other things should occur. So, quite a bit research has gone, and not only this, similarly about maintaining this structure, so about the raw material preparation, about the coke preparation. These are very important for a smooth functioning of the blast furnace. This gives an again idea again from a dissected blast furnace, the change in the composition of metal, droplet of metal and slag. So, these are sort of a sampling position from where they picked up the metal and slag droplets, and as you can see this is actually the sort of tuyer region. So, temperature is high in this region. So, carbon pickup by slag and metal is very high. So, it is a that is how you say the carburization of the carbon occurs here. So, which goes 4% or more. So, liquid metal always has carbon 4 to 4.5%. Similarly, the silicon pickup this is a bit erratic, but mostly silicon pickup is occurring becoming quite high in this tuyer and above in the Boss region and belly region, because this paper goes up and absorbed by the droplets of metal and slag, and silicon level increases in that one. So, you can see silicon level can go up to 3%, that is very high. So, you need a desiliconization. Sulfur pickup of course depending on the temperature and basicity and other thing of the slag. This sulfur content decreases as it goes near the hearth or tapping side, it continuously decreases. Of course, the manganese pickup is high, especially by the metal. So, manganese goes mostly into the metal. So, these are all samples which were taken out at various places in the blast furnace, operating one, and that shows the composition of all these important elements which are there in the metal and slag. and this gives an idea that how the situation prevails in the blast furnace, inside the blast furnace, and how one can improve it. Nowadays, in fact, you won't find silicon percentage of that high. This is again, as I said, all 4-decade old minimum 4-decade old dissection study. So, many improvement have occurred, and silicon goes very low now with the preparation of proper raw material and temperature and other thing. Now it can go easily 0.5% or so. So, finding from this dissected blast furnace, generally the ore layers and coke layers keep their edge charge stratification well in descending to the melting zone, which we have seen it, they are in the layer form and they descend maintaining that one. The lower part of the furnace where 3 or 4 ore layers are softened and fused together before melting. So, there it can thin down and they fuse together. And the other important feature, the top part where the layering is determined by charging method, burden material and size distribution. The lumpy zone where the individual particles of ore do not as that get fused together and the coke and ore layer make an orderly descent as stratified. So, as long as they are not fused and temperature is not very high, in a very orderly manner they descend into the lower portion. So, it does not pose that much problem to the permeability of the blast furnace and further reduction of the charge. The layer thickness decreases while the angle of inclination is also decreased as the burden descends. I think this you might have noticed this that you can see how big is the inclination angle in the starting of the layer, but as it comes down this decreases, and of course, the thickness is also decreasing of the layers. So, that is about the point which it says the cohesion zone is nothing, the cohesive zone where semi-fused molten metal is there, material where the ore is softened, fused and eventually melted is formed by the descending ore in accordance with the state of the gas flow that is in turn determined by the burden distribution and the position of the tuer. As we saw about the position of the tuer, the operation of the tuer has a profound effect on this softening of the material. The coke zone, which is situated beneath the cohesive zone and above the core or the conical deposit of the coke known as dead man, serving as the coke supply source for the combustion zone. So, this dead man is a very important if you look at the we have a raceway. So, and then we have a one coke conical shape which is just sitting over there extending up to the hearth, and that is called the dead man because it does not take part as such in any chemical reaction or other thing. However, it gives the mechanical support to the whole burden. So, that is very important and not only that, it also provides the permeability. So, all molten material is percolate through that, and it also supplies the coke for combustion. So, that dead man is a very important part of the blast furnace. So, it is about that which we are talking. So, the combustion zone is a zone of coke burning in and around the raceway in a swirling motion. The coke in the core, which is a deposit of coke in the conical shape, is found in the lower part of the coke zone, is being held up for a long time. So, this actually gets the coke in the dead man zone. It is like 14 days to 18 days or more it would be sitting there before it is replenished or replaced by the other coke. So, residence time is very long of the coke in the dead man. The melt bath, which is composed of slag layer on the top of the metal layer, is filled up with coke, which is often much coagulated near the bottom, and the bath itself fills the space between the lower portion of the core and the hearth. So, essentially all the slag and iron is sitting in between the holes of the dead man, and when the metal production is more and sometimes lots of metal is there in the hearth, this dead man floats on the liquid iron, because liquid iron density is about 7000 kg per meter cube, and the coke density is very low, about 800 or so, or in fact with the bulk density could go up to 500-600. So, it floats on the liquid metal, but not exactly when you start taking out the liquid metal, it sinks down. So, all the liquid metal and slag, it is sitting within the pores of the dead man, and then you drain it out. So, it acts like a strainer for this metal and slag.